Derivative can also be used to trace the curve or graph of the given equation. If we can find the relative maximum point, relative minimum point, and the point of inflections, if there's any, then the graph can also be drawn easily. We have relative maximum value at C if there exists an open interval containing C such that f of C is greater than or equal to f of x for all x in the given interval. We also have relative minimum value at C if there exists an open interval containing C such that f of C is less than or equal to f of x for all x in the given interval. And we have relative extremum value at C if C is either relative maximum or relative minimum. Graphically, this is your relative maximum and your relative minimum. A function is decreasing on an interval I if and only if f of x of 1 is greater than f of x of 2 whenever x of 1 is less than x of 2. Graphically, a function is increasing on an interval I if and only if f of x of 1 is less than f of x of 2 whenever x of 1 is less than x of 2, and graphically, this one. Function is a monotonic if it is either increasing or decreasing on interval I but not both. Suppose a function of f which is continuous on the closed interval AB and differentiable on open interval AB. We have the theorem number 1, if f prime of x is greater than 0 for all x in AB, then f is increasing on closed interval AB. And if f prime of x is less than 0 for all x in open interval AB, then f is decreasing on AB. Graphically, this one. Here are the steps on polynomial curve tracing. Step 1. Find the critical points. Step 2. Determine the direction of the graph and determine if there is a relative maximum or relative minimum. Step 3. Use the second derivative to find the concavity and the points of inflection if there's any. Step 4. Find the exact coordinates of the x and y intercept if there's any, the critical points and the points of inflection. Step 5. Combine all the evidence collected to graph the function and sketch the graph. Example. For step 1, from the definition, we say that x is equal to c is a critical point of the function f of x if f of c exists and if either of the following are true. The f prime of c is equal to 0 or the f prime of c doesn't exist. So from the function f of x is equal to 6x squared minus x raised to 4. The first derivative is 12x minus 4x cubed. Equate it to 0. That's why you have 12x minus 4x cubed is equal to 0. Let us get the GCF or the greatest common factor. You have 4x multiplied by 3 minus x squared is equal to 0. Equate both factors to 0. So we have 0 is equal to 4x, which will lead you to x is equal to 0. for the other factor, you have 3 minus x squared is equal to 0. Then you have x squared is equal to 3. Therefore, you have x is equal to positive and negative square root of 3. Therefore, the critical points are 0, square root of 3, and negative square root of 3. For step 2, let us determine the direction of the graph and determine if there is relative maximum or minimum. We have the number line with the critical points, negative square root of 3, 0, and square root of 3. From the interval negative infinity to negative square root of 3, take any value of x and substitute to f prime of x. We'll take x is equal to negative 3. But first, let us recall the first derivative. We have 4x multiplied by 3 minus x squared. When x is negative 3, the sign of 4x is negative. And the sign of 3 minus x squared is also negative. Negative multiplied by negative, the sign would give you positive. From the interval negative square root of 3 to 0, take any value of x and substitute to f prime of x. We'll take x is equal to negative 1. When x is equal to negative 1, the sign of 4x is also negative, and the sign of 3 minus x squared is positive. Negative multiplied by positive is equal to negative. From the interval of 0 to square root of 3, take any value of x and substitute to f prime of x. We'll take x is equal to 1. When x is equal to 1, the sign of 4x is positive and the sign of 3 minus x squared is positive. Positive multiplied by positive is also positive. From the interval square root of 3 to positive infinity, take any value of x and substitute to f prime of x. We'll take x is equal to 3. When x is equal to 3, the sign of 4x is positive and the sign of 3 minus x squared is negative. Positive multiplied by negative is negative. This is positive. Since this is positive, the direction of the graph for the interval negative infinity to negative square root of 3 is increasing. And this is negative. The direction of the graph for the interval negative square root of 3 to 0 is decreasing. And for the next interval, this is positive. The direction of the graph for the interval 0 to square root of 3 is increasing. And for the last interval, we have negative. The direction of the graph for the interval square root of 3 and infinity is decreasing. Using the first derivative test, the function y is equal to f of x is a maximum for x is equal to c if the f prime of x is greater than 0 for x is less than c, the f prime of x is equal to 0 for x is equal to c, the f prime of x is less than 0 for x is greater than c, and the function y is equal to f of x is a minimum for x is equal to c if the f prime of x is less than 0 for x is less than c, the f prime of x is equal to 0 for x is equal to c, and the f prime of x is greater than 0 for x is greater than c. If we're going to summarize this, or if we're going to use the information of increasing and decreasing. From increasing to decreasing, you have relative maximum at x is equal to c, or the critical point c. From decreasing to increasing, you have a relative minimum at x is equal to c. Let us determine if there is relative maximum or minimum. From positive to negative, from increasing to decreasing, it means relative maximum at x is equal to negative square root of 3. For the next critical point, x is equal to 0. From negative to positive, from decreasing to increasing, it means relative minimum at x is equal to 0. And for the next critical point, square root of 3, we have positive, then negative. From increasing to decreasing, it means relative maximum at x is equal to square root of 3. Step 3. Use the second derivative to find the concavity and the points of inflection. The second derivative is the rate of change of the first derivative. It follows that when the second derivative is greater than 0, the first derivative is increasing. And when the second derivative is less than 0, the first derivative decreases. The graph of y is equal to f of x is concave upward on any interval where the second derivative is greater than 0. And concave downward on any interval where second derivative is less than 0. Let us use the second derivative to find the concavity and the points of inflection. From the first derivative, 12x minus 4x cubed, the second derivative is 12 minus 12x squared. Let us factor this result. We have 12 multiplied by 1 minus x squared, or simply 12 multiplied by 1 minus x times 1 plus x. Let us equate these factors to 0. So we have 0 is equal to 12. For this factor, we don't have any solution set. That's why you have x is equal to empty set. And then for 1 minus x, it will lead you to x is equal to 1. And for the last factor, 0 is equal to 1 plus x. The value is x is equal to negative 1. Possible inflection of points are negative 1 and 1. A point where the sense of concavity changes is called a point of inflection. It can be shown that if y is equal to f of x as a point of inflection at x is equal to c, then second derivative of c is equal to 0, or the second derivative of c does not exist. Point of inflection test. Using the possible point of inflection, if f double prime of c is greater than or less than for x is less than c, and if f double prime of c is less than or greater than for x is greater than c, then y is equal to f of x as a point of inflection at x is equal to c. And also, if it doesn't exist, you have point of inflection at x is equal to c. Using the number line with possible point of inflections negative 1, 0, and 1. And also, let us recall the second derivative of the function 1 minus x and 1 plus x. From the interval negative infinity to negative 1, take any value of x and substitute to your second derivative. We'll take x is equal to negative 2. When x is equal to negative 2, the sign of 1 minus x is positive and 1 plus x is negative. Positive multiplied by negative is negative. From the interval negative 1 to 1, take any value of x and substitute to the second derivative. We'll take x is equal to 0. When x is 0, the sign of 1 minus x is positive and the sign of 1 plus x is also positive. Positive multiplied by positive is positive. From the interval 1 to positive infinity, take any value of x and substitute to the second derivative. We'll take x is equal to 2. When x is equal to 2, the sign of 1 minus x is negative and the sign of 1 plus x is positive. Negative times positive is negative. For the interval negative infinity to negative 1, it is concave down. For the interval negative 1 to 1, it is concave up. And for the interval 1 to positive infinity, it is concave down. Using this information, let us check if the change of concavity. We have negative and positive. There is a change of concavity, therefore, negative 1 is a point of inflection. And let us check for the other possible point of inflection. We have positive and negative. There is a change of concavity, therefore 1 is a point of inflection. Step 4. Find the exact coordinates of the x and y intercepts, if there is any, the critical points and the points of inflection. Recall that the f of x is equal to 6x squared minus x raised to 4, or can be written as y is equal to 6x squared minus x raised to 4. For x-intercept, let y is equal to 0. We have 0 is equal to 6x squared minus x raised to 4. Factor the expression, we have 0 is equal to x squared multiplied by 6 minus x squared. Equate both factors to 0, so we have 0 is equal to x squared, which leads to x is equal to 0. For the other factor, we have 0 is equal to 6 minus x squared. Then we have x squared is equal to 6. Get the square root of both sides. The value of your x is positive and negative square root of 6. The coordinates of x-intercept are 0, 0, square root of 6, 0, and negative square root of 6, 0. For the y-intercept, we are going to substitute the value of x is equal to 0. When x is equal to 0, we have y is equal to 6 multiplied by 0 raised to 2 minus 0 raised to 4. Y is equal to 0. The coordinates of y-intercept is 0, 0. For the critical points, we are going to substitute the values of 0, negative square root of 3, and square root of 3. For x is equal to 0, we have y is equal to 6 multiplied by 0 raised to 2 minus 0 raised to 4. The value of y is equal to 0. When x is equal to negative square root of 3, we have y is equal to 6 multiplied by negative square root of 3 raised to 2 minus negative square root of 3 raised to 4. The value of y is equal to 9. When x is equal to square root of 3, we have y is equal to 6 multiplied by square root of 3 raised to 2 minus square root of 3 raised to 4. The value of y is 9. The critical points are 0, 0, negative square root of 3, 9, and square root of 3, 9. For the points of inflection, we are going to substitute negative 1 and 1. When x is equal to negative 1, we have y is equal to 6 multiplied by negative 1 raised to 2 minus negative 1 raised to 4. The value of y is equal to 5. When x is equal to 1, we have y is equal to 6 multiplied by 1 raised to 2 minus 1 raised to 4. The value of your y is also equal to 5. The points of inflections are negative 1, 5, and 1, 5. For step 5, we are going to combine all the evidence collected to graph the function. Graph the x-intercept, graph the y-intercept, graph the critical points, and graph the inflection points. From negative infinity to negative square root of 3, we have increasing. From negative square root of 3 to 0, we have decreasing. And from 0 to square root of 3, we have increasing. And from square root of 3 to positive infinity, decreasing. The graph now would be this.